So the fourth step in our structural elucidation process is using NMR spectroscopy, and it's got to be the organic chemist's favourite tool. In fact, we're going to talk about two sorts of NMR spectroscopy. There's what we call proton or hydrogen NMR spectroscopy, and there's also carbon-13 NMR spectroscopy. They give you different clues for solving the puzzle. In fact, let's talk about carbon-13 NMR spectroscopy first, and let's turn to the VCE Data Booklet to see what sort of information we have at our disposal before we look at a spectrum.
The tables that you see here come directly from the VCE Data Booklet, and you can see that there are different functional groups. That's in the left-hand column, and I've split the table in two, so there's nothing specifically different between the left-hand side and the right-hand side. I've just squeezed them onto a single page, and you can see that it sort of goes in ascending order of chemical shift. Alkanes and so on, they typically tend to be at these very low values. As you get higher and higher, the carbons are more likely to be next to an oxygen atom or next to a nitrogen atom, involved in a double bond or a triple bond. And at the very high values for chemical shift, almost getting towards 200, you're looking at carbon atoms that are involved in a carbonyl group, so a ketone, an aldehyde, a carboxylic acid, and so on.
So in this carbon-13 NMR spectrum, you can see we have 3 peaks. Now, 2 of the peaks are quite low in terms of their chemical shift. They're down towards sort of 20, 40 ppm. So these are quite indicative of, if you like, an alkane type of environment. So a CH3 group, a methyl group, maybe a CH2 or a CH group, which are a part of if you like, what we call an aliphatic chain, or an alkane type of chain, which might be part of a bigger molecule. In fact, this is clearly a bigger molecule because it's also got a peak right up near, almost near 200. Now, this is always indicative of a carbon atom, but that is in one of those carbonyl groups, so it's double bonded to an oxygen atom. You can see it's got a very different chemical shift. So this molecule might be a ketone, aldehyde, carboxylic acid, so it's got those aliphatic bits or the alkane type of bits, but somewhere else in the molecule there's a carbonyl group from one of those functional groups I just mentioned. To get further information, we're going to have to turn to proton or hydrogen NMR spectroscopy.
So again, turning to the VCE Data Booklet, and I've got about 3 whole pages of NMR data here for proton NMR, you can see the different characteristic chemical shifts corresponding to different functional groups. Now, we've arranged these in increasing chemical shifts. So at the lower values, you can see, once again, there's the alkanes, CH3 groups, CH2. But then as you go up in chemical shift, you can see that we've got some slightly different characteristics. If a methyl group is next to a carbon, which is in a carbonyl, you can see that this increases to about 2 ppm. If you're talking about a haloalkane, in other words, it's like an alkane, but it's got a halogen, a fluorine, a chlorine, bromine, and so on, you can see that that proton's chemical shift is now up towards 3 to 4.5. Again, if it's next to an OH group, about 3.3 to 4.5. And as you go through the table, you can see that as that carbon environment becomes, if you like, more complex, it's near oxygen atoms, nitrogen atoms, this characteristic chemical shift changes. One of the really strange ones that we see in proton NMR spectroscopy are OH groups or NH groups. These can vary considerably, and it depends on different conditions. And of course, our old friend hydrogen bonding has a lot to do with this. Just like the OH stretch band in infrared spectroscopy, we saw, unlike all the other bands, it's really wide, it's really broad. Similarly, in NMR spectroscopy, these OH and NH bands, they're really broad, they're spread out across a range of chemical shift. Sometimes they're spread out so much that they flatten and you don't even see them in the NMR spectrum. You can see alkenes are getting up towards 4.5 to 7. An OH group, which is from a benzene ring, can be anywhere from 4 to 12. But most importantly, as we get towards the hydrogens that are on benzene rings that are associated with carbonyl groups, these start to go up to very high values for chemical shift. And by high, I mean anywhere from 8 to 13. You can see in this table, the very last one, carboxylic acids, really characteristic, up towards 10 ppm.
For the same molecule we were looking at earlier with the carbon-13 NMR spectrum, here's the proton NMR spectrum. And you can see it's got a series of different peaks. And something that's quite different with hydrogen NMR spectroscopy is you get these splitting patterns where individual peaks are split into doublets or triplets. In fact, this NMR spectrum has what's called a septet. So the peak has been split into 7 different peaks. Now, the peak on, if you like, the far right-hand side, or it's at the lowest chemical shift, this is really typical, just above 1 ppm, typical of an alkane environment. Whereas the septet, it's a little bit further downfield, in other words, at a higher value for ppm, or the chemical shift. Now, it's not quite clear what this could be. You've got to go back to those data tables to have a think about what sort of possibilities you might have in that case there. And then the final peak, of course, is right up near 12, which is really indicative of an OH group. In fact, it's most indicative of an OH group in a carboxylic acid rather than an alcohol. And if you think about the clues that we got from the infrared spectrum, that checks out. The infrared spectrum we were talking about in the previous video seemed to be suggesting it was a carboxylic acid. These spectra are for the same molecule, so you can see how the puzzle is all starting to come together.
In this video here, you can see my colleague, Dr. Clint Woodward, preparing an NMR sample. The first thing he's doing here is taking the molecule of interest and putting it into a small vial. But to measure the NMR spectrum, you don't typically measure the sample in a pure form. It needs to be dissolved in a solvent. Of course, here's the catch. Most solvents themselves have hydrogen atoms. So to avoid getting those hydrogen atoms measured in your NMR spectrum as well, the solvent that Dr. Woodward is adding here is a deuterated solvent. In other words, rather than hydrogen atoms, atoms which have 1 proton and no neutrons, he's using deuterium atoms with hydrogens that have 1 proton and 1 neutron. These don't get picked up in an NMR spectrometer. You can see here he adds it to the long tube. It's about 15 centimeters long. And once it's ready, gets a small cap, puts that on top, and the sample's ready. From here, it's simply a case of introducing it into the top of the NMR spectrometer. You can see here the spin solve. Doesn't need long. Click the button to acquire the sample, and you've measured your NMR spectrum.
So that brings us to the end of our 4-part series of videos which talk about the process of structural elucidation. Don't forget about the workbook that goes along with these videos. If you don't have a copy of that, you can get in contact with me. You'll find my email address in the notes. Beyond this, I'm going to hand it over to your teachers to work through the activities and teach you more about techniques for using spectroscopy to determine molecular structure. Good luck.